All right, so welcome everyone to this talk number 6 in the series ONEPAS on the PDEs of quantum mechanics. And today it's a pleasure to have Peter Hislop from University of Kentucky talking to us about eigenvalue statistics for some random Schrödinger operators and random band matrices. Thank you very much, Peter.
Thank you very much. I'm really happy to give this talk here to discuss some developments over the last 20 years or so concerning random Schrödinger operators. And part of my talk also is going to be on some work concerning random band matrices and sort of similarities between both of these. Primarily, I want to focus on the localization-delocalization transition, in particular for some special models. So this always happens. I was hoping I could flip up my screen. Sorry about that. I've had this much easier to do that. Want to write on it. So basically my talk will be divided into 4 parts. First, for those of you who might not be too familiar, I'll just review some basics about Schrödinger operators and random Schrödinger operators and remind you about the density of states, which plays a very important role in the local point processes that I'll describe. In the second part of the talk, I'll talk about what the local eigenvalue statistics are, how you formulate them, and some of the conjectures for random Schrödinger operators in general dimension. And also give you some idea of what's known in one regime, in the localization regime. Reasonable amount is known, but in the delocalization regime, if it exists, very little is known. But there are 2 models that I wanted to describe and at least exhibit some of the aspects of these models that do show a transition. And the first one is a model of a one-dimensional lattice Schrödinger operator with a particular type of disorder, which I'll call a scale disorder. And in fact, it's known that there is a transition in the local eigenvalue statistics for this model, and I'll describe some aspects of that. And a second model I wanted to talk about is the model of random band matrices. Again, there's a long-standing conjecture about a transition in the local eigenvalue statistics, and I want to describe some recent work, both by another group, other people in the delocalization regime, and I'll talk about some recent work in the localization regime. And for those interested, I'll talk about, have some references to this work. So let me just begin with the general setup of Schrödinger operators. The linear transformations I'll talk about are exactly that. They're linear, no nonlinear operators in this particular talk. And our basic Schrödinger operator always it be written as the sum of 2 parts. So a linear self-adjoint operator H0, which is the background operator. It could be the Laplacian. It could be the Laplacian plus a periodic potential. Those are the 2 common cases. What I'm most interested in is the potential function V omega, which is in fact a random process. And I'll describe typical examples, Anderson type potentials in just a moment. In general, the work will be described for either the lattice model, so that is on L2 of ZD. It has some advantages. For example, typical kinetic energy is bounded, makes some of the estimates easier. It's also a bit more transparent. On the other hand, the continuum model on big L2 of RD has some really interesting challenges, even in describing the localization aspects of that Schrödinger operator. They were studied second after the lattice models, and I'll mention those. However, for the general flavor of the results, you can keep one or the other in mind. So as I mentioned, the H0 is deterministic, it's fixed, it'll be self-adjoint. A little bit later, I will talk about the covariance property of these operators. In addition to being a self-adjoint operator, it has to have a certain covariance, for example, translational invariance like the Laplacian, or invariance with respect to some lattice if it's the Laplacian plus a periodic potential. And that has to be compatible with the properties of the random potential. So it can't be an arbitrary fix. For example, a Stark Hamiltonian would not fit into this framework, or a Zeeman Hamiltonian, magnetic field or electric field wouldn't fit in. Although if you do it with a fixed magnetic field. So you have a Landau Hamiltonian that can fit into this framework. The random potential, if you describe it on the lattice, it acts locally. So if K is a lattice point, K is in ZD, then the potential acts on a function at the point K simply by multiplying by a random variable omega K. So you have a family of random variables, omega K, and the K belongs to every point of your lattice. On the other hand, the continuum model, the corresponding projection onto a site, of course, is singular in the Hilbert space we're working on. So you smooth out the direct analog of the lattice model to a bump potential. And so you can think that every point has a potential U, which is some fixed given function of compact support that's been translated to all the sides of the lattice. And again, it interacts with the potential through the random coupling constant omega sub k. The details of these models will not be that important for the rest of the talk, and many of you are aware of them. Just if the typical situation is when the potential is non-negative, that guarantees some monotonicity properties of the spectrum with respect to the random variables, which is technically quite important for some of the estimates. If you've never seen this type of Schrödinger operator before, in fact, what I've described is an uncountable family of Schrödinger operators in the sense that for each omega now, the symbol when I write omega, I mean a collection, omega sub k. If I just take a set of real numbers associated with each point on the lattice, that gives you a configuration of the potential. And the randomness comes in by saying that we're going to let those configurations of the potential vary with respect to a probability measure. Okay, so it's really a family of operators. And they're all self-adjoint. We'll assume in this slide that the randomness, at least in the beginning, is such that the potential will be bounded. So we'll take the coupling constants first to be independent and identically distributed. We'll take them to be distributed according to a probability measure on, let's say, an interval. If you want to keep some model in mind, consider the interval -1, 1, and rho is a probability measure on that interval that's absolutely continuous with respect to Lebesgue. So it's got a density, and in fact, I'll call rho the density of that measure. That's the simplest case. You can think of on the lattice, or even in the continuum, you can think of Bernoulli distributions and so on and so forth. But I'll stick to the case where the probability measure has a density that's compactly supported and even smooth. Later at the end of the talk, I'll talk about Gaussian distributed random variables. And of course, there, the support is the entire real line. Okay. Covered those. The covariance property that I mentioned before is really essential in order to study this family of Schrödinger operators, because you think, well, if I fix an omega, I got a spectrum of that self-adjoint operator. I change omega, the spectrum is going to change, and so on and so forth. So it seems like a problem that is non-tractable, because you've got uncountably many self-adjoint operators, and you got a spectrum for each one. The covariance property is the one thing that saves you, because all you want to know with probability 1 is that the spectrum of these operators are all the same. And Pasteur and others back in the 70s realized that if you have the probability space equipped, of course, with a probability measure, and if you have an action on that that is an ergodic action with respect to that measure, and that also lifts to the Hilbert space that you're working on, and your Schrödinger operator has the property that the lifting to the action on the Hilbert space is implemented by a unitary transformation, and the Schrödinger operator has this covariance property with respect to that unitary transformation, then in fact, you can talk about the spectrum of the random family. In the simplest case, the action that we're talking about when we have IID random variables, the probability space is just the infinite product space, and the measure is the product measure. And of course, since they're identically distributed as you translate from one point k to k plus to its nearest neighbor and so forth. You have a natural action on the probability space, and the measures I described, being the infinite product measure, is actually ergodic with respect to that action. And in fact, the usual translations on the Hilbert space, just taking j to j plus k, are implemented unitarily, of course, and the Schrödinger operator described, just take the Laplacian plus v omega for h omega. It satisfies this covariance relationship that it's unitarily equivalent to the same Schrödinger operator, but with the shifted random variable. So you think omega, and then you shift all of them to one site. That's the key covariance relationship. The main consequence for us, well, actually there'll be two. The first one is that given the family, there exists a closed subset of the real line that's independent of omega, so that for almost all omega, the spectrum of this family of Schrödinger operator h omega is equal to sigma. And that set sigma is called the deterministic spectrum. So at least you can spend time talking about what's the nature of the deterministic spectrum. You know, is it pure point, AC, and so on and so forth. Actually, I'm not going to speak about that. There is a whole other parallel discussion about spectral transitions for random Schrödinger operators. I'm going to look at the spectral statistics transition, which I'll go on to describe. But that's always in the background.
Peter, before you change the slide, so about terminology, by coupling constant in the lattice case, you mean potentials?
Yeah, so V omega on a function at the site k is simply multiplied by that random variable times the function at the site k. Right, so really the potential is given by this countable family omega sub k. Okay, to talk about local eigenvalue statistics, and also many aspects of these of Schrödinger operators, it's very convenient to work with self-adjoint operators with discrete spectrum. You can talk about their eigenvalues. And of course, this is done by restricting them to cubes. So lambda sub L will be a generic cube in RD or in ZD of side length L. And we want to take our Schrödinger operator H omega restricted to L with self-adjoint boundary conditions. So I'll just write that as H super lambda, the box sub omega. And the spectrum of this is discrete for the models that I've described. In the lattice case, it's a finite number of eigenvalues. It's the size of the box, so you have that many eigenvalues. In the continuum case, of course, if you're using the Laplacian and restrict that, let's say to a box with Dirichlet boundary conditions, there are infinite number of eigenvalues. But at least we have a discrete spectrum. Okay, so that's the first thing to get off the ground. I mentioned that ergodicity was important for two things. One is the deterministic spectrum, and the other is for the existence of the density of states. And that's what I want to describe, starting with our Hamiltonians that have been restricted to a box. So basically, if you take a fixed interval, and of course, this only makes sense if I intersect sigma is not equal to the empty set. Take such an interval and take the spectral projector for the self-adjoint operator restricted to the box and simply count up the number of eigenvalues, take the trace of that in that box, take its expectation and divide by the volume. And so that will be a deterministic quantity since I've taken the expectation, and I call that the local density of states measure, right? It's a renormalized counting function for the eigenvalues. And in fact, ergodicity guarantees that the existence as the volume goes to infinity exists, that the limit exists, and that defines the density of states measure. And that measure, of course, depends on the single site probability measure rho, which is telling us how omega at a certain site or any site varies. Okay, so that's the density of states measure. and it'll play an important role in the local eigenvalue statistics. There are two related quantities to this measure, mu sub rho. It's a probability measure. The distribution function is perhaps the more familiar integrated density of states. So basically, it's counting up the number of eigenvalues less than a fixed energy E, okay, renormalized and taking the limit as the volume goes to infinity. And very often, this measure mu rho is absolutely continuous with respect to the Lebesgue measure. So it has a density, and that density is called the density of states function. It's the Radon-Nikodym derivative of the integrated density of states with respect to the energy. And that quantity, we're always going to assume, given the hypotheses that I mentioned, that will exist for these models, and it plays an important role, as I mentioned. Okay, so given the Schrödinger operators, random Schrödinger operators, their restriction to boxes, so we have a discrete spectrum, we can introduce the local eigenvalue statistics. Basically, we want to know how these eigenvalues talk to each other, how they interact, how that interaction is determined by the probability distribution that we started out with. And of course, we want something that is almost sure, so we will average and take the limit of the local volumes to infinity. And that will be the local eigenvalue statistics that I want to talk about in the rest of this talk. So just a review here. So the main object is the counting function, in a sense, the function that lives on rescaled eigenvalues for the local Hamiltonian. So I've introduced notation that E sub j super lambda of omega are the random variables that are the eigenvalues, right, of H lambda omega. In the lattice case, there are n of them, if that's the size of the box, or in the continuum case, there are infinitely many. And what I want to do is I want to fix in the spectrum sigma, I want to fix an energy E0, and effectively I'm going to be looking at the eigenvalues in a neighborhood of E0 that have been centered and rescaled. And so the rescaled and centered eigenvalues appear down here in the argument of this delta function. So I rescale by the volume after I center the eigenvalues at 0. So what I hope is that this measure, which is just a sum of direct delta functions localized at these rescaled eigenvalues, that this measure will have some limit in the volume that lambda goes to infinity. So we start out with a local point process of the rescaled eigenvalues. Of course, it's a random point measure on the real line. If we're in the lattice, it's just in some finite region of the real line. And we want to ask, does that family of random measures have a limit, and how do I characterize that limit? Now, this rescaling for random Schrödinger operators actually comes from another estimate I'll mention a bit later called a Wegener estimate, which tells us that the mean spacing between these eigenvalues in the large volume regime goes like 1 over the volume. So we rescale the eigenvalues in a neighborhood of E0 by this quantity, the volume of the region lambda. Okay, so this is going to be the key quantity. You can think of it as a random measure, or as it's a random point process. And just to give you an idea again here, what the rest of this talk will be about will be for various models and for various choices of E0. Does this random point process converge to a point process as lambda goes to infinity? So that would be a point process on the real line. How do you characterize it? And there are some answers known in the general setting that I've been describing. Does it converge? Well, yes. provided that E0 is in a certain regime. That's been proved, although there are conjectures for all choices of E0 in the deterministic spectrum sigma. And how do you characterize the limiting point process? And that depends on both the dimension of the model and on where this E0, right, where we've localized the statistics to where that's located in the deterministic spectrum. So I'm not going to spend my talk describing in detail the results, but I did want to mention what general results exist for random Schrödinger operators. The conjectures go back probably to the 50s when theoretical physicists started looking at the effect of impurities on conductivity in disordered systems. That is, you take a lattice of a perfect crystal, which is a lattice of atoms, and you add discontinuities or impurities. So you disorder it somehow. How does that affect the conductivity? Probably most people are aware of Anderson's pioneering work in that field. I wanted to think about two regimes in the deterministic spectrum sigma that are characterized in terms of how the system in a box looks at different scales. So I have a box of side L, and I also have another scale which comes from the localization length of the eigenfunctions. And what's very important is to look at the ratio of the localization length of an eigenfunction to the size of the box and how that scales as you take the volume of the box to infinity. And so I'm going to roughly, this is a heuristic argument, but roughly going to say that in the localization regime, this ratio of localization length of a typical eigenfunction to the size of the system, that if that ratio goes to 0, as the size of the system goes to infinity, that's, I'm going to call that the localization regime. And if we choose our centering energy, E0, in that regime, so for which the eigenfunctions basically have this property, then it's conjectured that the limiting point process is a Poisson point process. And basically that says that things act very, very independently. There are no correlations between the eigenvalues, because after all, these eigenvalues depend upon all values of omega j inside of the box, so they're highly non-independent. However, in this regime where this type of ratio is achieved, they begin to behave independently, and so the Poisson statistics is a characteristic of independence. On the other hand, if the scaling is such that the localization length is more or less the same as the size of the system, so the eigenfunctions look extended as opposed to being very localized, you expect something else to happen. So in the regime where the ratio of the localization length to the size of the box remains bounded below, or may actually diverge to infinity, what was conjectured is that the limiting point process has the same statistics as a random matrix ensemble, the Gaussian orthogonal ensemble, at least if the dimension is 3. Dimension 2 is controversial, even amongst the theoretical physicists. And in dimension 1, I'll just mention, the random Schrödinger operators are always localized, and you have only a localized regime. So you always get Poisson statistics in that case, regardless of where you place E0. So those are the conjectures.
Peter?
Let me see. Any questions? Sure.
Sorry. So I guess this implies that all the eigenvalues, they are all of the same localization roughly. And so they are all in the same regime. Is that right? If you fix E0, all of the eigenfunctions, sorry, are more or less either all localized or delocalized?
No, only in the neighborhood where I'm working, right? So I'm rescaling, so I sort of stay in a fixed interval about E0 in rescaling.
You should have a lot of eigenfunctions but this implies that they should all have more or less the same localization.
Right, they more or less in the local neighborhood, they all are localized with good probability with the same localization length.
Thanks.
Good probability. That's in the case, first case I mentioned. The second case, in the examples that I'll discuss, you have extended states in this, so that the states are spread out almost maximally on the scale capital L. So you have the opposite behavior. And so they get the opposite. So in some sense there, the eigenvalues, people say the eigenvalues are repulsed. They don't act as if they're independent. They really feel their neighbors and they don't like to be, it's a COVID situation. They don't like to be near their neighbors. And that's very characteristic from work of Wigner in the 50s of these Gaussian orthogonal ensembles and the Gaussian unitary ensembles. You have eigenvalue repulsion. So another measure, which I'll say a little bit about, not just the rescaled point process that I've been describing, you might ask, what about the nearest eigenvalue spacing, the level spacing distribution? It's another signature way, another statistic for these models. So roughly speaking, if you focus on the equation down here, you look at the difference between two consecutive eigenvalues of our localized system. You rescale again by the volume, and you can rescale by the density of states function at our fixed local energy E0 and divide by the number of eigenvalues in some window. Then that level spacing distribution should also undergo a transition. In fact, this is well known to people working in random matrix theory. The limit does exist as the volume goes to infinity, and its behavior depends upon whether E0 is in this localized region or in the delocalized region. In fact, if you open up Mehta's book on random matrix theory, you can't help but see these famous graphs. So in the Poisson regime, the density that one's interested of that's related to the level spacing distribution is exponential. So you have no rule on the sort of average rule on the spacing between consecutive eigenvalues. Some are close together, some are far apart. You don't have the COVID repulsion. On the other hand, if you look at the associated density for the matrix ensembles like GUE or GOE, it's well known that you have eigenvalue repulsion, and you can see that by looking at these corners that the eigenvalues don't like each other, they're repulsed. And the signature of GOE is that you start out with this curve is linear, and GUE, it's quadratic. So that's what you expect in this other regime for random Schrödinger operators, at least if the dimension is 3 or more. So the results to finish the second part are sort of meager, you might say. On the localization side, we now know a lot. We know that for lattice models, Minami proved in 1996 that the limiting local eigenvalue statistic is a Poisson point process, as it was conjectured. That was studied and generalized a lot by the work of Germanet and Klopp several years later, and who also proved that the level spacing distribution is exponential in the localized regime. For continuum random Schrödinger operators, the technical difficulties I mentioned earlier had prevented a lot of work for a while. It was first shown by Nakano that the limiting point process is in fact an infinitely divisible point process, which is good because the GOE is not infinitely divisible. In work with Krishna, we proved that in fact the limiting eigenvalue statistics always have limit points in the continuum models. And in fact, they are compound Poisson processes. What we were lacking at that time is something called a Minami estimate, which is a way of calculating the probability that two eigenvalues for the local system are close together. And that's always been a problem with continuum random Schrödinger operators. And much more recently, Dietlein and Elgaard proved a very, very nice result for Anderson type random Schrödinger operators, L2 of RD, a Minami type estimate, which allowed them to prove that the local eigenvalue statistics is a Poisson character, at least very much near in an interval of energies near the bottom of the spectrum. On the other hand, if you ask about delocalization, well, at least from eigenvalue statistics, almost nothing is known. So big open problem there, despite a lot of effort. So now I'm going to go to the second half of my talk and talk about two models for which we can say an awful lot more about the questions that I've just raised about the local eigenvalue statistics. So the first model is a scaled disorder model, and it's in one dimension. Now you might remember that I said a while ago, in one dimension, we only expect localization. That's true for the ergodic random Schrödinger operators on the line or on Z. So this model is a modification of that, and it's cooked up in such a way that my heuristics about localized regime and delocalized regime can actually be computed and can be seen. So it's a hybrid type model, but it does exhibit a transition in the nature of the local eigenvalue statistics. So it's a 1D model, and it's constructed the following way. Instead of lambda as being a box in ZD, I'm going to look at intervals, of course, from -n to n in Z, right? So I just take number of points from n -n to n. And so I'm going to take that Hilbert space. Now I realize my notation is slightly ambiguous when I say interval -n to n. I really mean at -n to n intersect the lattice, right? So this is a lattice model. So I take my Laplacian finite difference operator, and then the potential. I have my random variables up in the numerator, and now I'm going to rescale the random variables by the size of the interval. So I'm going to divide omega j's by n to the power alpha. So that'll give me a new parameter alpha that I'll be able to play with and see how that affects the local eigenvalue statistics. And PJ, I remind you, is just the projection onto site J in the lattice. Okay, so it's the same model, but the rescaling of the disorder by the length. Okay, so what happens is that as I take n larger and larger, of course, the random variable omega j always stays the same. I don't change the probability measure for the omega j's, but I weaken them by dividing by 1 over the size of the interval to the power alpha. And so I have this new parameter alpha in the model, and that's what makes the difference. You can compute what the localization length is of the eigenfunctions on the interval -n to n intersect Z. And it turns out that the localization length scales like n to the power 2 alpha. Now the size of the box is n. So when I compute the ratio that I discussed earlier in the conjectures, it's n to the power 2 alpha minus 1. And so we automatically see, and I'll show on the next slide, that the regimes that I was describing are obtained for this scale disorder model. And that's why it's so interesting, right? So you get the various scaling regimes. So if alpha is between 0 and 1/2, then our ratio, so I remind you that gamma n over n is equal to n to the 2 alpha minus 1. So if alpha is between 0 and 1/2, then this ratio goes to 0. So the conjecture now for the scale disorder model is that you get Poisson statistics if you take take alpha less than a half. And if you take alpha bigger than a half, then of course this ratio in fact is always bounded below by 1 and goes to infinity. And you should expect a different eigenvalue statistics in that regime. Now looking at the potential, the way that I've scaled it, of course, as n goes to infinity, the randomness in the potential drops out. So you would expect for this toy model that the statistics that you get taking n to infinity of the scale disorder model should be the same as the statistics of the Laplacian, and that was nicknamed clock statistics by Barry Simon years ago, who studied similar phenomena for ergodic, including random Schrödinger operators on the lattice. And clock statistics is very nice because it's characterized, if I look at the level spacing distribution I mentioned for scale n and scale by n, then when you take this limit, the limit goes to a constant. So you think of this as being rigidly, the eigenvalue repulsion is rigid. The eigenvalues are at least 6 feet apart, right? And that's characteristic of, that's the clock distribution. And so this actually goes to 1 over the density of states function at the energy E0, where you're looking at the nearest neighbor spacing around E0. So these are the conjectures. If alpha is less than a half, you get Poisson. Bigger than a half, you get clock. When alpha is equal to half, it's the critical scaling. And that was studied extensively by primarily probabilists, Krzyzewski, Valko, and Virag, who analyzed in detail the process that you get at the critical exponent, alpha equal to a half. It's a very interesting point process that in fact has stronger eigenvalue repulsion than, for example, the classical ensembles. Okay, well, they did not study, although they understood what was happening for alpha less than a half and alpha bigger than a half. So with Frederick Klopp, we've been studying that, and also Fushiyama Nakano has been studying it for the last 10 years. I just wanted to spend a few moments to describe how do you do this? How do you compute these local point processes? And what are the key ingredients that you use in order to prove the limiting process is, for example, Poisson? So Poisson, again, is the hallmark of independence. These eigenvalues for h in an interval of length 2n are definitely not independent. So what saves you is the fact that the eigenvectors really do live in small regions, much, much smaller than the size of the interval, which is 2n. And consequently, the spectrum of the operator on the interval of scale n is reproduced in the eigenvalue spectrum of Schrödinger operators on smaller boxes. And the Hamiltonians, the Schrödinger operators on smaller non-overlapping boxes are independent. So you can map the eigenvalues that are not independent to eigenvalues of Hamiltonians on smaller boxes that are independent and compute the process using the Hamiltonians, the spectra of the Schrödinger operators on the smaller scale. And so the way to do that is to choose a new scaling exponent that's bigger than the one that you fixed. Alpha is between 0 and a half. And remind you that the localization length is 2 alpha. And so what you want to do is to break up our interval minus n to n into boxes that are not too small, because you want to capture the eigenvectors, or at least most of the eigenvectors that live on a scale of size n to the power 2 alpha. So n prime is the size of these guys, whereas the big scale is n, and there you expect to be able to get many of the eigenvectors localized. Okay, so you do this local decomposition, you have your smaller scale, n prime scale Schrödinger operators, And the localization estimates on scale n, which are classical results that tell you basically that the matrix elements of the Green's function decay exponentially in the difference between the two, in the difference between the two localization sites. And I'll write this down in a few minutes explicitly. Those localization estimates imply this correspondence that every eigenvalue for the Schrödinger operator on scale n in a fixed interval is very, very close on a much smaller scale to the eigenvalues of these Schrödinger operators on scale n prime, right? Because their eigenvectors almost look the same. So you do perturbation theory and the eigenvalues are very close, good enough to get an estimate. And the eigenvalues on the smaller scale n prime, as you change from one interval of length n prime to the next one in this decomposition, they're all independent families. And so it's this independence that you use to prove the Poisson eigenvalue statistics. So the conclusion of the localization estimates is with a good probability, you have this correspondence. And so now you have these families of independent eigenvalues and you're asked, well, how do you get from those guys to Poisson statistics? And you use the very well-known Poisson-Bernoulli limit theorem that says that if you have a bunch of Bernoulli random variables that are independent, let's say capital N of them, and you know that the probability that one of these random variables is equal to 1 is P sub n, then in fact, this well-known Bernoulli expression converges to the exponential law, that is to say the probability of finding k of these, right? So P sub n is the probability of one of these random variables taking value 1. So the probability of having k of them take a value 1 is lambda k divided by k factorial times e to the minus lambda, where lambda now becomes the intensity of the point process. That holds provided you can prove that the probability that a Bernoulli random variable is equal to 1 times the number of random variables you have has a limit as lambda goes to infinity. So in fact, we're going to use this for these eigenvalues that are independent in order to prove the Poisson statistics. And the one thing that we need are the independent Bernoulli random variables, and here they are. So on the smaller scale n prime, you simply take this random variable to be 1. If the local Hamiltonian on scale n prime has 1 eigenvalue in a fixed interval and 0 otherwise. So as this index j varies from one of the sites up to all the other subintervals, this is a family of independent Bernoulli random variables. And so I want to ask, what's the probability that k times this occurs? That is to say that the probability that a local Schrödinger operator at scale n prime has an eigenvalue in the interval, that the number of those eigenvalues in the interval is equal to k. Well, I can bound that above by saying that the Bernoulli random variable is equal to 1 for k points. So I have again this big interval from minus n to n, and I've divided it up into a certain number of intervals, capital N prime. And so at k of these points, here, 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 they have 1 eigenvalue in the interval, and the rest of them you have 0. That immediately gives you this Bernoulli expression. And the final thing to prove that finishes this outline of the proof is the critical estimate that the probability that the Bernoulli random variable is equal to 1, that's P sub n prime, times the number of quantities independent sites that you have, which is capital N prime, that converges to something. And what does it converge to? Exactly what I mentioned. It converges to the density of states function for the Laplacian at energy E0 times the length of the interval. And that's actually the intensity of the Poisson point process. And so the conclusion is you apply the Poisson limit theorem to get Poisson statistics with an intensity given by the density of states of the limiting operator, which is the free Laplacian. And the law is given here exactly from the Bernoulli Poisson limit theorem. So that's how the localization of the eigenfunctions allows you to introduce or to find a rich family of independent Bernoulli random variables and prove then that the limiting process is Poisson. There are other techniques in the other regime when alpha is equal to, when alpha is bigger than a half, which allows you to conclude the other conjecture that the limiting point process is the same one as for the Laplacian, which is this clock process. And in the last part of my talk, so that is the scaled disorder model. It is a random Schrödinger operator. It, of course, is not ergodic. It is one-dimensional, but it does show that you can construct a non-trivial model where you can see a transition in the local eigenvalue statistics. And for that reason, it's a lot of fun to work with and pretty interesting. So the last part of my talk, I want to mention some recent work that I've been involved with about localization and the statistics for random band matrices. Another situation where we have conjectures about a transition and a lot has been realized. So random band matrix, you should think of that as a 2n plus 1 by 2n plus 1 matrix. Basically, it's easy to draw a picture of it. You have the diagonal, and then you have non-zero entries in a band. And then outside of the band, you have zeros. So the classical ensembles of random matrices that I'd mentioned before is the case when the band is maximal, when the width of the band is the same as the size of the matrix, which is 2n plus 1. A true band matrix is when you're less than that. Okay, so the width of the band I'll call W 2L plus 1. So you have N and you have L. And the entries are rescaled so that the sum of the variances on any row or any column is equal to 1. So you scale by 1 over the square root of the width. And then the VIJs are independent identically distributed. Of course, they're independent up to symmetry because I want these to be self-adjoint matrices. They're zero outside of the band. And you can think of these as being Gaussian distributed. That's the classical case, but you need not do that. So the Gaussian case, the expectation is 0 and the variance is set equal to 1. So the variance of the entries, the omega ij's, is 1 over, right? 1 over of the matrix elements, I should say, is 1 over the square root of the width. And that plays an important role. That's somewhat similar to the scaling in the disorder, as you'll see in a moment. As I mentioned, there are two extremes. If you take the width to be 1, so you have a diagonal matrix with the independent identically distributed random variables down the diagonal, that's very much like a 1D Jacobi matrix. If you take the Laplacian plus a random potential on L2 of Z, then if you just have the nearest neighbor Laplacian, what you get, the potential elements are, omegas on the diagonal, and then you get ones in the off diagonal. You get this tridiagonal matrix. But it's very similar because if you take the width to be equal to 1, you just have the randomness on the diagonal and you have complete localization. If you take the width to be 2n plus 1 maximal, the way I've described it, you have the Gaussian orthogonal ensemble. And you have complete delocalization that's been known since back to Meta's time and even before Meta. It's all summarized in Meta's book on random matrices. So the band matrices are sort of interpolating families, sort of what makes it kind of interesting. And for the rest of the remainder of my talk, the width is going to scale like the size of the matrix to a power alpha, and alpha between 0 and 1. So very much like the scaling of the disorder in the previous Schrödinger operator model. And as you might expect, there are conjectures, right, as to how the statistics behave with regard to the ratio of the width to the size of the matrix. So again, for alpha less than a half, you expect you're in a localization, you get a Poisson point process situation, and the eigenvectors are exponentially localized. For alpha between a half and 1, the limiting point process should be GOE, and the eigenvectors should be extended. So again, it's a model that exhibits localization, delocalization transition. So what's been known about that? Unlike the scale disorder model, it's the flip. The delocalization regime has been extensively studied and is much better understood than the localization regime. So there's a series of pioneering works by Bourgade, Yao, and Yin and co-workers where they prove for the width bigger than n to the power 3/4. So this is in the regime where n alpha is bigger than a half, where you have delocalization, that indeed the eigenvectors are extended with very good probability, that the density of states function is given by the so-called semicircle law with very good probability. And you can also, they also prove that the k-point correlation functions for the eigenvalues approximate those given by the k-point correlation functions for the Gaussian orthogonal ensemble. A really beautiful work. There's still work that can be done for experts in random band matrices because they're a bit far from the conjectured regime down to a half. On the other hand, for alpha between 0 and a half, I should point out that these random band matrices are the analog of D equal to 1 random band matrices that I'm labeling just by the elements of Z. There is, in fact, localization at all energies for these models. And you can use a lot of the machinery developed for random Schrödinger operators, at least to get crude estimates on probabilities that you have eigenvalues in given intervals. So-called Wegener estimate that I mentioned is the probability of the matrix having an eigenvalue in a small interval. The Minami estimate is the probability of a matrix having 2 eigenvalues in a small interval. And because the eigenvalues are not independent, it's not just the square of the previous estimate. And then the localization bounds. So to finish up, let me just say something about it. Here again are these estimates I mentioned earlier. What's the probability you have at least 1 eigenvalue? It scales like the size of the matrix and like the interval of energy that you're looking at, and the width to the 1/2 power. And in fact, Pellet, Shamus, Schenker, and Soden improved that in the Gaussian case that you can eliminate this 1/2. And that's especially important when you have the growing width as n increases. And then an upper bound on the probability of 2 eigenvalues in an interval is so-called Minami estimate. And I'll just finish some recent work with a student, Ben Brody. We first looked at the local eigenvalue statistics when the width is fixed. When the width of the band is fixed and you take the size of the matrix to infinity, you actually have a limiting operator, just as in the Jacobi matrix case. And that makes some of the work easier. Most of the technical work involved in extending the ideas I mentioned is centered on finding the intensity of the point process, that is, in controlling the density of states for this model. to finish up here is a picture of the localization bound that I mentioned several times earlier. You take the Green's function and you look at its matrix element between two basis vectors at j and at k. And basically that decays exponentially. That's a signature of localization for random Schrödinger operators. And let me say the density of states function is defined the same way. What we were able to prove was the convergence of the finite n density of states function to the infinite density of states function. In fact, uniform convergence in the energy. And that allowed us to get a handle on the point process defined exactly as previously discussed. So the rescaled eigenvalues centered at an energy E with a rescaled energy interval. And then we were able to prove that the probability of, actually this should be the expectation, I'm sorry, not the probability, of the trace of the spectral projector actually converges to the limiting density of states function at energy E times the interval. And that gives us the proof that the limiting point process is a Poisson point process and identify the intensity of the process. So that's the end of the overview. There are a lot of similarities between the scaled disorder and the random band matrix model. So these theorems that I concluded with are only for alpha equal to 0 when you have fixed bandwidth. And I'll just mention in some recent work with Krishna, we've been extending these results to the regime alpha between 0 and 1/2, where now the width is growing as the matrix is growing. So once again, there's no limiting n equal to infinity operator. That thing makes things a bit more complicated. The other thing which I'd like to mention is that the localization bound, primarily due to Schenker and then extended by Peled, Schenker, Shamus, and Sodin, is known only for alpha less than 1/7. But if we assume that it's known up to the critical alpha 1/2, then in fact, we believe that we can prove that the limiting local eigenvalue statistics is indeed Poisson, and we can compute what the intensity of the limiting process is. So I'll end there. Thank you very much for your attention and for the opportunity to speak. And if anyone's interested, I can send you this. There are a set of references here in these notes, and of course it's being recorded. Maybe I should leave it here. And thank you very much.
Thank you very much, Peter. So are there questions for the speaker?
Hi. So few slides back, you had a theorem for localization at all energies.
Right.
So in the bound, there was a constant which depends on the sort of the bandwidth. In the Gaussian case, do you think that constant is going to be independent of the bandwidth?
So here's what I can tell you. That was a good observation. So this is for alpha equal to 0.
Mm-hmm.
Okay, when alpha is not equal to 0, you have to go to these bounds proved by Jeff Schenker and then extended. And what you get is the width. So this is a fractional moment bound. These bounds were introduced by Eisenman and Molchanov 20 some odd years ago. And they are one of the ways, very, very effective ways of proving Anderson localization type properties, both for these models, for many random graph models, and for random Schrödinger operators. And so what you get, and this alpha is as small as between 0 and 1, you get the width to the power s, and then you get e to the minus a constant which is relatively computable that does that. Let me not write. I can explicitly show you its dependence. Let me erase that. So a constant depends on s. depends on S, and it depends on the energy, the real part of the energy. And then it's going to be J minus K, and then it's going to be divided by the width to the power S times mu. That's how it depends. So the width is scaling like n to the alpha. Oh, sorry, just there's no S in the denominator. There, okay, erase. No S there, it's mu. And in the optimal case, if I want to get a bound up to a half, alpha equal to half, mu is going to be equal to 2. So this is going to be n to the 2 alpha. So that's what they prove. And they only prove this for alpha. They prove it for mu equal to 7 instead of 2. And so that means alpha has to be less than a seventh. I hope that partially answers your question. That's the bound. Now, we would like to actually eliminate that. It would give us a much better estimate. But we don't, I mean, at the moment, we don't know how to even prove this beyond a seventh. That answer your question?
Yeah, thank you very much.
Yeah. I'm happy to discuss that in more detail if you'd like.
Sorry, I just had one question. It's a little vague, but so if I understand well, if you have finite or bounded width, then you have a limiting operator as you take and go to infinity.
It's this tridiagonal matrix, right?
And if you let it grow slowly, then there is no limit object, maybe not an operator, but some other, like there is nothing you can work with. You have to say things.
Well, the thing that we can work with is that it was proven by Pastor, Molchanov, and Karunji back in the early, I don't know, in the 80s, that the limiting density of states is a semicircle given by the semicircle law. And that's what we work with, that you have convergence, weak convergence of the density of states to the semicircle law. That's characteristic of these growing bandwidth matrices. And you are actually, they also know that it goes like 1 over the width for the finite volume. It's a semicircle law with error that goes like 1 over the width, 1 over the bandwidth as the n goes to infinity. But, you know, I can't say there's no infinite operator. It's possible that some sort of infinite operator exists. But I mean, that's intriguing. I mean, there may be another setup. That's a very intriguing question.
Okay.
I mean, at the moment, we think we found a proof that works up to a half, provided you have this estimate, this Schenker estimate. But that's one could speculate. Very nice. Yeah.
Peter, in your definition of the scale disorder model, somehow I felt it was a bit unnatural definition, that you should have divide by j to the power alpha rather than n by power alpha.
Well, you're not alone in that thought, because that's another model which we can treat, which I called the decaying disorder model.
Exactly, yeah.
And so in fact, the techniques here for alpha less than a half apply to that model. I'm just trying to scroll back here. And I didn't want to introduce that today. So omega j, what Michael's suggesting is omega j divided by j to the alpha. Right, times the projector on site j.
Your more natural things, because
yeah,
it exists for any n, it's independently of n.
So everybody who works on these models, the 3 groups who have worked on this model, treat both of them. So and it's an excellent observation, right? And so you get different at the critical alpha equal to a half. Krzyzewski and Valko and Virag proved the statistics again, and you get a different statistics. You get a beta Hermitian ensemble in statistics for this decaying disorder model, as opposed to here, where you get something, a new type of statistics I call the Schrödinger tau model, where the beta and tau are constructed out of parameters of the model. Right. And of course, yeah. So here you do have a transition also. So it's
Okay, then dimension, why you can look at other dimensions, not only one. So why is there special reason for one?
For these scaled models,
Yeah.
You can prove in, let's see, for the decaying, this model has been studied in higher dimensions for the decaying randomness model. And I mentioned there are results that if it decays faster than alpha equal to 1, so for alpha bigger than 1, and then you might guess scattering theory comes in, and you can prove that the local eigenvalue statistics do converge, and they're given by the statistics for the free operator, because the potential decays so rapidly. It's scattering theory. Actually, the deep result in that direction is that Bourgain years ago proved for Gaussian randomness for this model that if you're between just bigger than a half, so in the range which was interesting, between a half and 1, Bourgain proved that the wave operators actually exist, and therefore that you have AC spectrum for this model. And that was incredibly deep result of Bourgain.
And thresholds are independent of dimension. This 1/2 and 1 are independent of dimension.
Yeah, actually Bourgain's result is in 2 dimensions.
Dimension, I see, okay.
Right. He has some results in higher dimensions, but they're weaker.
Right, okay.
The 2-dimensional result is really great. And I'm not sure it's been exploited. It's a very deep proof.
Right.
But it proves the wave operators exist almost surely, which is something you would like.
Right. And of course, there are lots of related equations like perturbation by looking at the nonlinear operators, for example.
Yeah, there's some work. You worked on that years ago. Actually, I had a student work on it, and Justin, is he still home? He's quite interested. He's worked on that. Maybe I guess Avi Sofer has recently worked on that. So right, with the nonlinear Schrödinger equation, the general question is: you take nonlinear Schrödinger equation, so let's say it's focusing cubic. The question I'm interested in is: does randomness destroy the soliton profile if the randomness is strong enough? And I guess results of Avi, and actually a student and I worked on this, that if you have a bounded potential that's small in some sense, you have some stability. And that's what you worked on also, right, Michael? You had some stability under bounded perturbations. If you crank it up, can you destroy the soliton?
Right.
I hope that's what you were probably doing. And that I think is really interesting. And I don't know, except for Avi's got some recent papers on this. I don't know of others. So that's, for cubic and LS, for example, even just in 1D.
Right.
That's really, really. So Benoit, we got some non here.
I don't want to go into it, but also there's relation to topology, right? So if you have periodic Schrödinger operators perturbed by the random ones.
Yeah, I mean, a lot of the standard stuff, if your background operator H0 is minus Laplacian plus V periodic, right? As long as your random potential has this compatibility with respect to an ergodic action, so the period has to be compatible with the randomness or vice versa, which is true in the standard models. Then you have, if your randomness is very weak, as you know, you can prove that the bands, at least the bands that are not overlapping, of course, grow a little bit and you have band edge localization for that type of model. Is that what you're thinking of?
Yeah, but there is also so-called what's the block bundles and the relation to the topological insulators and so forth.
Yeah, I don't know that, right. I don't know if let me just think. I don't know if people have looked at. So you think of a hexagonal, for example, and you add some randomness to it, or you take one of these ones that recently studied where you cut it along edge.
Yeah, that's another.
Yeah, I don't know. Am I missing? Has that been studied by anyone?
I don't know. I'm asking you. So.
It's a very good question. I sort of have a student looking at some of that stuff, and I don't. Anybody know of any results on that? There's a slew.
The Jacob Shapiro should know.
Yeah, I'll talk to him.
Localization is a prerequisite to have the topology or topological invariance well defined. So you have that.
Right.
Otherwise, usually you study the localization properties of these models using the same tools, like finite moment analysis. Sorry, fractional moment analysis.
Yeah. This more or less standard localization technique should hold. It's a lattice model, or even continuum model, but to get finer analysis that could be.
With some caveats, for example, in 1D, you might not have complete localization.
Right.
Okay,
Is that something you work on, Fabio? Is that Fabio who was talking?
No,
sorry.
I was planning to say that maybe that we should kind of stop recording and let people off and then have informal.
Well, let's thank the speaker again then, and then we can continue our discussions later. Thank you very much for this talk.
Thank you.
Yeah, thank you very much.